Now, the most important method in sequence and series is method of difference. Now, this method of difference will be used when the general term can be expressed as difference of two consecutive values of another sequence. So, if we have a sequence whose nth term can be expressed as fn minus fn minus 1, or maybe fn plus 1 minus fn, then this sum, it becomes easy using telescopic summation. So method of difference is a method where you're going to write a term as a difference of two successive terms of a sequence, and telescopic summation is a summation method where terms cancel out. So generally for telescopic summation, you need method of difference first to express this nth term as a difference of two successive terms. So let us take up an example. Say for example, we have to find sum of this series where r varies from 1 to n, 1 upon r into r plus 1. Now, this is your rth term. We can write it as 1 upon r plus 1. We can write this as r plus 1 minus r upon r plus 1. Now we can separate them, and the first term r plus 1 will cancel. We write 1 upon r, and in the second one r will cancel. We write this as 1 upon r plus 1. Now this is method of difference. Now we'll need to find the sum, and we'll find the sum using telescopic summation. So if we write our first term a1, so we'll put the value of r as 1, so it'll be 1 upon 1 minus 1 by 2. Second term, we'll put r as 2, it'll be 1 by 2 minus 1 by 3. Third term, 1 by 3 minus 1 by 4. And nth term, it'll be 1 by n minus 1 upon n plus 1. Now, we need to find the sum, and sum is nothing but sum of all these terms. So it'll be a1 plus a2 plus a3 up to an. And if we add them, all these successive terms, they'll cancel out, leaving this first and the last term. So sum of the series will be simply 1 minus 1 upon n plus 1, or simply n upon n plus 1. So method of difference is basically creating this structure where eventually in the telescopic summation, terms cancel out. Now we can also use shortcut for telescopic summations. So your an, it could be either fn minus fn plus 1, or it could be an equals fn plus 1 minus fn. Now, if we look at this first summation, so this Sn will be this summation AR, where R varies from 1 to n, and there will be A1, and A1 will be F1 minus F2, then F2 minus F3. I'll go on till Fn minus Fn plus 1. Now here F2 will cancel, F3 successive terms will cancel, and this Fn will also cancel. So in this case, we can write this Sn as directly F1 minus Fn plus 1. Say for example, we have this summation. Summation k varies from 1 to n, 1 upon k minus 1 upon k plus 1. So this is 1 upon 1 minus 1 upon 2, then 1 upon 2 minus 1 upon 3. So it is of the form Fn minus Fn plus 1. So here we can directly write this Sn as F1. So we'll put k as 1 here. So it will be this 1 minus fn plus 1. So fn plus 1 will be when we put either n plus 1 in this or n in this one. So it will be 1 upon n plus 1. So we can directly write it as n upon n plus 1. Now sometimes this an, it could be of the form fn plus 1 minus fn. Now in this case, if we're going to write Sm, it will be this summation r varies from 1 to n ar, it will be f2 minus f1, then f3 minus f2, and in the end it will be fn plus 1 minus fn. Now here, all these terms, they'll cancel. We'll get this as fn plus 1 minus f1. So here we'll have this Sn as fn plus 1 minus f1. So it depends whether it is fn minus fn plus 1 or it is fn plus 1 minus fn. Now if we consider an example, suppose we have this summation. Summation k varies from 1 to n k plus 1 square minus k square. So clearly in this case, fn is n square. So this result will be fn plus 1, which is n plus 1 square minus f1, and f1 is simply 1. So you can directly use the summation. Now both these summations, we have assumed that they start from r equals 1, but it may not be necessary that you're going to start with the first term. So if you want to write in general, if we have this ARS FR minus FR plus 1, and we have to find this summation R varies from M to N AR, it will be this summation R varies from M to N FR minus FR plus 1, which will be Fm minus Fn plus 1. And if m is 1, it will be same as F1 minus Fn plus 1. And for the second case, if AR is FR plus 1 minus FR, then this summation R varies from M to N AR, it will be this summation R varies from M to N FR plus 1 minus FR, and here it would become Fn plus 1 minus Fm. But personally, I do not like to use shortcut for two reasons. First, you don't get this feel of telescopic summation if you're using a shortcut. And also, there are so many problems where you may have, especially in recurring relation problems, where you could have telescopic summation on one side and on the other side you are having some other summation. So it's always better to write it in expanded form and solve it rather than using a direct shortcut. Now we already know these formulas. Summation R varies from 1 to n. Summation R, it is n plus 1 by 2. Summation R varies from 1 to n R square. This is n plus 1 to n plus 1 by 6. And then this is summation R varies from 1 to n R cube. This is n plus 1 by 2 whole square. Now we have already proved this first one. We can prove the other two results using principle of mathematical induction. So one way of solving these two is using principle of mathematical induction, which you can do yourself. Now I'll prove these two results using method of difference. Now what we know is r cube minus r minus 1 cube. So a cube minus b cube will be a minus b into a square plus b square plus ab. So it will be this 3r square minus 3r plus 1 and say this is your AR. Now we need to find Sn, which is this summation AR, where R varies from 1 to n. So it will be the summation R varies from 1 to n R cube minus R minus 1 cube, and it'll be this summation 3r square minus 3r plus 1. And for brevity, I'm dropping the index and the end values. Now, if we look at this, if r is 1, this is 1 cube minus 0 cube. When r is 2, it is 2 cube minus 1 cube. It'll continue, and in the end, it'll be n cube minus n minus 1 cube. Now, this is nothing but this is telescopic summation. So all these terms, they'll cancel out. So on the left hand side, we'll just have n cube, and this is 3 times summation r square minus 3 times summation r plus summation 1. Now we need to find summation r square. So we can write this as 3 times summation r square. It is equal to n cube plus 3 times summation r minus summation 1. So this is n cube, and this is 3 times n plus 1 by 2. And this is simply n. So this is 3 times summation r square. It will be, we'll take this n common, or we'll take n by 2 common. So it'll be this 2n square plus 3n plus 3 minus 2, or this summation r square is n by 6, 2n square plus 3n plus 1. Now we can factorize this as 2n square plus 2n plus n plus 1. So it'll be this n plus 1, 2n plus 1 whole divided by 6. And that's the formula for summation r square. So summation r square is n plus 1, 2n plus 1 by 6. Likewise, you can prove summation r cube equals n plus 1 by 2 whole square. And for this, you'll need this AR as r to the power 4 minus r minus 1 to the power 4. Now this is a plus b, a minus b. So it'll be r square plus r minus 1 square. And it'll be r square minus r minus 1 whole square. So this AR will be r to the power 4 minus r minus 1 to the power 4. Now this is 2r square minus 2r plus 1. And here will be 2r minus 1. Or this AR will be r to the power 4 minus r minus 1 to the power 4. And this is 4r cube minus 2r square minus 4r square plus 2r plus 2r minus 1, or simply AR as r to the power 4 minus r minus 1 to the power 4. So it will be this 4r cube minus 6r square plus 4r minus 1. Now if we take this summation, we'll use telescopic summation here. So it'll reduce to n to the power 4. And here we'll get this as 4 times summation r cube minus 6 times summation r square plus 4 times summation r minus summation 1. And using this, we can prove summation r square will be equal to n plus 1 by 2 whole square. So I'll leave this calculation part onto you. Now here the question is, we need to find some of these 4 series. Now this first one is, we are given this series which is 1 into 4 into 7, 1 upon 4 into 7 into 10, 1 upon 7 into 10 into 13, we need to find its sum up to nth term and then up to infinity. Now first we'll find nth term for this series. Now this is 1, 4, 7. It's an AP. So its nth term will be a plus n minus 1, and common difference is 3. So there'll be 3n minus 2. So it will be this 1 upon 3n minus 2, 3n plus 1, and 3n plus 4. Now basically this question is method of difference. Now difference between 1 and 7 is 6, 4 and 10 is 6, 7 and 13 is 6, and 3n minus 2 and 3n plus 4 is 6. So what we'll do is we'll multiply and divide everything with 6. So we can write S as 1 by 6, and this is 6 upon 147, and this is 6 upon 4710 up to 6 upon 3n minus 2, 3n plus 1, 3n plus 4. Now this is 1 by 6. Now we'll write this 6 as 7 minus 1. So it will be this 7 minus 1, and this is 147. Here we'll write this as 10 minus 4. This is 4 into 7 into 10. Here it is 13 minus 7. This is 7 into 10 into 13. And here it is 3n plus 4 minus 3n minus 2. So it will be 3n plus 4 minus 3n minus 2 upon 3n minus 2, 3n plus 1, 3n plus 4. And what we'll do is we'll split these terms. So you can write this is 1 by 6. Now here 7 will cancel. So it is 1 4 minus 4 7. Now here 10 will cancel. It will be 4 into 7, and here 4 will cancel. 7 into 10. Here 13 will cancel. So this is 7 into 10 minus 10 into 13, and will continue. And here this 3n plus 4 will cancel. So it will be this 3n minus 2, 3n plus 1 minus, and here 3n minus 2 will cancel. So it will be 3n plus 1 and 3n plus 4. Now if we look at these terms, these successive terms, they'll cancel. Now here we have this first one, then what remains is this last term. So this sum, it will be 1 by 6 into 1 by 4 minus 1 upon 3n plus 1 into 3n plus 4, and that is the sum up to n terms. Now if we find sum to infinite, we'll simply need to take this limit n tends to infinite Sn. Now if we take this limit n tends to infinite, this entire expression will be simply 0. So sum of this limit up to infinity is 1 by 24. So that is the answer to this first part. Now this second question is find the sum of the series up to n terms. So this series S is summation r varies from 1 to n, r plus 1, r plus 2, r plus 3. Now one way of solving this question is by taking this product, and then we'll have r to the power 4 r cube, which is very lengthy way of solving this question. So what we'll do is we'll write its rth term as r plus 1, r plus 2, and r plus 3. Now we'll try and use method of difference in this. So the term before this one, it will be r minus 1, and term after r plus 3 will be r plus 4, and the difference is 5. So what we'll do is we'll multiply and divide everything with 5. So we can write 1 by 5, and this is r plus 1, r plus 2, r plus 3 into 5. Now we want to write this as 1 by 5, and this is r plus 1, r plus 2, r plus 3, and we'll write this as r plus 4 minus r minus 1, and we'll split it in two parts. We can write 1 by 4, and this is r plus 1, r plus 2, r plus 3, r plus 4, and minus, and this is r minus 1, r plus 1, r plus 2, r plus 3. So that's our rth term. Now we can write this first term as 1 by 5, and this is 1 into 2 into 3 into 4 into 5 minus, and this is 0. We can write its second term as 1 by 5, and this is 2 into 3 into 4 into 5 into 6 minus, and this is 1 into 2 into 3 into 4 into 5. Third term is 1 by 5, and this is 3, 4, 5, 6, 7 minus, and this is 2, 3, 4, 5 and 6, and its nth term is 1 by 5 n plus 1 n plus 2 n plus 3 n plus 4 minus n minus 1 n plus 1 n plus 2 n plus 3. Now Sn is sum of these first n terms, so we'll add them. We can write this Sn as t1 plus t2 plus t3 up to tn. Now here these terms, they'll cancel. Now here we have this left, so here what remains is this expression, so it'll get cancelled. So it'll be this 1 by 5 into n plus 1 n plus 2 n plus 3 into n plus 4, and that is the answer to this question. And since Sn is proportional to n, S infinite will be infinite. So as n approaches infinite, this sum is going to diverge. Now this third one is this summation. R varies from 1 to n, 1 upon 4 r square minus 1. So it will be this summation. R varies from 1 to n, and this is 2r minus 1, and this is 2r plus 1. Now here difference is 2, so what we'll do is we'll multiply and divide everything with 2. So it will be the summation. R varies from 1 to n, and this is 2 upon 2, and this is 2r minus 1 and 2r plus 1. Now we can write this as this summation. We'll take 1 by 2 common, and here will be this r varies from 1 to n, and we can write this as 2r plus 1 minus 2r minus 1 divided by 2r minus 1 and 2r plus 1, which is 1 by 2, and then this summation r varies from 1 to n. Now here 2r plus 1 will cancel, so it will be this 1 upon 2r minus 1, and here 2r minus 1 will cancel, and this is 2r plus 1. So we can write this sum of n terms as 1 by 2. Now we put r as 1, it will be 1 upon 1 minus 1 by 3, r as 2, so it will be 1 by 3 minus 1 by 5, and we continue up to 1 upon 2n minus 1 minus 1 upon 2n plus 1. Now 1 by 3, 1 by 5, they'll cancel. So here we have this first term, so we'll have this last term. So this Sn, it will be 1 by 2, 1 minus 1 upon 2n plus 1, or this is n upon 2n plus 1. Now we find S infinite, it will be this limit n tends to infinite, n upon 2n plus 1, and since this is infinite limit, answer to this limit is coefficient of highest power of n in the numerator and in the denominator. So it will be this 1 and 2. So sum of the series up to infinity is 1 by 2. And then we have this fourth one, which is this series Sn. So this is 1 by 4, 1 into 3, and this is 4 into 6. This is 1 into 3 into 5, and this is 4 into 6 into 8, and goes up to n terms. Now for nth term we'll have 1, 3, 5. So it is an AP. So its nth term will be a plus n minus 1 into d. So there will be 2n minus 1. And here this is 4, 6, 8, which again is an AP. So this is a plus n minus 1 into d, which is 2n plus 2. 4, 6, 8, and this is 1, 3, 5. What seems to be missing is 2. So what we'll do is we'll multiply and divide everything with 2. So we can write this Sn as 2 into, and this is 2 into 4, and this is 1 into 3, and this is 2 into 4 into 6. This is 1 into 3 into 5, and this is 2 into 4 into 6 into 8, and this is 1 into 3 into 5 up to 2n minus 1, and here it will be 2 into 4 into 6 up to 2n plus 2. Now, if we write its general term will be rth term and will be this 2 into and then 1, 3, 5 up to 2r minus 1, and in the denominator will be 2 into 4 into 6 up to 2r plus 2. Now, because we have to use method of difference, somehow we have to express it as sum a minus b. So we have to introduce a minus b into this. So what we'll do is we'll write this as 1 here, and we can write this 2, and this is 1 into 3 into 5 up to 2r minus 1, and we can write this as 2r plus 2 minus 2r plus 1 whole divided by 2 into 4 into 6 up to 2r, and this is 2r plus 2. Now what we'll do is we'll split it in two parts. Now we can write this as tr, and this is 2. Now for this first part, 2r plus 2 will cancel, so we get this as 1 into 3 into 5 up to 2r minus 1 upon 2 into 4 into 6 up to 2r, and then minus, here it is 1 into 3 into 5, and this is 2r plus 1 upon 2 into 4 into 6 up to 2r plus 2. So that's your tr. Now if we write t1 will be 2, and here it is 1 by 2 minus, and this is 1 into 3 and 2 into 4, because if we put r as 1, this is 2 and this is 4, and here it will go up to 3. Now if we put t as 2, so it will be this 2. Now this is 1, 3, and this is from 2 to 4 minus, and this is 1, 3, 5, 2, 4, 6, and it will continue like this, and this nth term will be 2, and this is 1, 3, 5, 2n minus 1 upon 2, 4, 6, 2n minus, and this is 1, 3, 5, 2n plus 1 upon 2, 4, 6, 2n plus 2. Now Sn is sum of all these n terms. So if we add them, we'll get Sn. Now here these successive terms, they'll cancel, and since we have this term here, what will remain is this last term, so it'll cancel. So it'll be this 2 into 1 by 2 minus 1 into 3 into 5 up to 2n plus 1 upon 2 into 4 into 6 up to 2n plus 2. And we find its sum up to infinite, it will be this limit n tends to infinite Sn. Now it will be this 2 into 1 by 2 minus, now here number of terms is n, and here number of terms is n plus 1. So here in the denominator, power of n will be greater, so it will be simply 0. So answer to this series will be 1. And that is the answer to this question. Now in this question, we need to find sum of the series up to n terms, and the series given is 1 upon x plus 1 plus 2x upon x plus 1, x plus 2, and this is 3x square upon x plus 1, x plus 2, x plus 3, and continue up to n terms, and the nth term will be n x to the power n minus 1 upon x plus 1, x plus 2 up to x plus n. Now what we'll do is, for this second term, we'll add x square and subtract x square. Here we'll add x cube and subtract x cube, and here we'll add x to the power n and subtract x to the power n. So we can write 1 upon x plus 1, and here if we take x common, it will be x plus 2 minus x square upon x plus 1, x plus 2. Here it will be x square, x plus 3 minus x cube upon x plus 1, x plus 2, x plus 3. I'll continue up to x plus n, x to the power n minus 1 minus x to the power n upon x plus 1, x plus 2 up to x plus n. Now what we'll do is we'll split each term in two parts. So we can write 1 upon x plus 1, and here x plus 2 will cancel. It will be x upon x plus 1 and minus x square upon x plus 1, x plus 2. Here x plus 3 will cancel. So it will be x square upon x plus 1, x plus 2, and then all other terms. And here x plus n will cancel. So there will be x to the power n minus 1, x plus 1 up to x plus n minus 1 minus x to the power n upon x plus 1 up to x plus n. Now here all these terms, they'll cancel. So what we're left is with these terms and this term. Now 1 plus x upon 1 plus x is 1. So this s will be simply 1 minus x to the power n upon x plus 1, x plus 2 up to x plus n. So that is the sum up to n terms. Now the second question is, we are given this sum a1 upon 1 plus a1 plus a2 upon 1 plus a1 into 1 plus a2 plus a3 upon 1 plus a1, 1 plus a2, 1 plus a3, and it goes all the way up to an upon 1 plus a1 into 1 plus a2 up to 1 plus an. Now in this also we need to introduce a negative sign. So what we'll do is we'll add 1 and subtract 1. So we'll add 1 and subtract 1 in each of the terms except this first one, and then we'll split each term in two parts. So we can write this sum as a upon 1 plus a1. Now here a2 plus 1 will cancel. So it'll be 1 upon 1 plus a1, and then minus it'll be 1 upon 1 plus a1 into 1 plus a2. In the same way, a3 plus 1 will cancel. So it'll be 1 upon 1 plus a1, 1 plus a2, and then minus 1 upon 1 plus a1, 1 plus a2, and 1 plus a3. I'll continue, and in the end we'll have minus 1 upon 1 plus a1, 1 plus a2 up to 1 plus an. Now all these successive terms, they'll cancel. So what we'll get is these first two terms and this last term. Now a plus 1 upon 1 plus a1, this is a1. So it is 1. So this sum will be 1 minus 1 upon 1 plus a1 into 1 plus a2 up to 1 plus an. And that is the answer to this question. Now here the question is, we are given this relation which is an equals an minus 1 plus 1 upon an minus 1 for all n greater than 1, and it is given that a1 it is equal to 1. Now it says we need to show that a75 will lie between 12 and 15. Now a1 is 1. If we write a2 is 1 plus 1. So a2 will be 2. a3 will be 2 plus 1 upon 2, which is greater than 2. And since it is an increasing sequence, any an will be greater than 2 for all n greater than 2. Now we look at this given condition. Now it says an equals an minus 1 plus 1 upon an minus 1. Now we square it, we can write an square as an minus 1 square plus 1 upon a n minus 1 square plus 2. Now we know that this is always greater than a n minus 1 square plus 2, because we are leaving out this positive term 1 upon a n minus 1 square, and we know that any a n it is greater than 2, then 1 upon a n will be less than 1 by 2, or 1 upon a n square will be less than 1 by 4. That means it will always be less than 1. So we can write it will be less than a n minus 1 square plus 3. So from here we can write a n minus 1 square plus 2 will be less than a n square, and will be less than a n minus 1 square plus 3. Now we can also write this as 2 is less than a n square minus a n minus 1 square, and will be less than 3. So we have this relationship that difference of squares of any two successive terms of the sequence will lie between 2 and 3. Now we'll start with n as 2. So we can write 2 is less than a2 square minus a1 square, and will be less than 3. And if we put n as 3, we'll write a3 square minus a2 square will be less than 3. And for n equals 4, we'll get a4 square minus a3 square will be less than 3. And we'll continue up to an square minus an minus square will be less than 3. Now if we add them all up here, this a2 square will cancel, a3 square will cancel. So all these terms will cancel. We can write 2 plus 2 plus 2 n minus 1 times. So there will be 2 n minus 1 will be less than an square minus a1 square, and will be less than 3 plus 3 plus 3 n minus 1 times, and there will be 3 n minus 1. Now we are given that value of a1 is 1. So we can write 2 n minus 1 plus 1 will be less than an square, and will be less than 3 n minus 1 plus 1. So this is the result that we have from the given condition. Now it says we need to prove that A75 will lie between 12 and 15. So what we'll do is we'll put the value of n as 75. So we'll put n equals 75. So this is 2 and this is 74 plus 1 will be less than A75 square, and will be less than 3 into 74 plus 1. Now this is 149. It is less than A75 square, and will be less than 223. Now we know that 149 is greater than 144 and 223 is less than 225. We can write 12 square is less than A75 square and will be less than 15 square, or A75 will lie between 12 and 15, and that is the answer to this question. Now the sixth question is, we are given the sequence of real numbers defined as u1, it is 1, and un plus 1, it is un plus 1 upon un for all n greater than or equal to 1. Now if we find u2 is going to be 1 plus 1, it will be this 2. u3 will be 2 plus 1 by 2, 2.5. So any ui, it will always be greater than or equal to 2 when I is greater than or equal to 2. Because we are adding something to un and it is clearly an increasing function. Now what you're going to do is we're going to write this as un plus 1 square will be un square plus 1 upon un square plus 2, or un plus 1 square minus un square will be equal to 2 plus 1 upon un square. And this is the iterative relation we are going to use for our telescopic summation. Since we need un, we are not going to start with n plus 1, we are going to start with un. So we can write un square minus un minus 1 square will be 2 plus 1 upon un minus 1 square. Next one will be un minus 1 square minus un minus 2 square, and that will be 2 plus 1 upon un minus 2 square, and will continue up to u2 square minus u1 square, and that will be 2 plus 1 upon u1 square. Now if we add all of them, then these successive terms they'll cancel, so we can write un square minus u1 square, and here this is 2 plus 2 plus 2, and it is from 1 to n minus 1 times, so there will be 2 n minus 1, and plus this is 1 upon u1 square plus 1 upon u2 square up to 1 upon un minus 1 square. Now u1 is 1, so this is 1, so we can write un square minus 1, and here will be this 2n minus 2 plus, now this u1 square again will be this 1, and this u2 square, u3 square and un minus 1 square, we know that any ui is greater than 2 when I is greater than or equal to 2. So 1 upon ui will be less than or equal to 1 upon 2, or 1 upon ui square will be less than or equal to 1 by 4 for any I greater than or equal to 2. So for all these terms from 2 to n minus 1, we can write this summation I varies from 2 to n minus 1, 1 upon ui square, it will be less than or equal to, now this is 2n minus 2 plus 1 and plus, now this is 1 by 4, 1 by 4, 1 by 4, n minus 2 times. So it will be this n minus 2 by 4. So we'll take this one on the right hand side. So this 1, 1 and 2 will cancel. So we can write un square will be less than or equal to, now this is 2n plus n minus 2 by 4, or we can write un square is less than, now this is 9n minus 2 by 4, now this 9n minus 2 by 4 will be less than 9n by 4. If we take square root both sides, we can write this un, it will be less than 3 by 2 under root n, and which is what we need to prove in this question. Now here the question is, find the sum of the sequence, and it is 1 upon 1 plus 1 square plus 1 to the power 4, 2 upon 1 plus 2 square plus 2 to the power 4 plus 3 upon 1 plus 3 square plus 3 to the power 4 up to n terms. Now what we are going to do is we are going to write its general term, its rth term. Now for the first term we have 1, for the second term we have 2. So for this rth term we'll have this r, and it will be 1 plus r square plus r to the power 4. Now what we'll do is we'll add r square and we'll subtract r square. We can write this as r upon, and this is a plus b whole square. So it will be 1 plus r square whole square minus r square, which is a plus b into a minus b. So it will be r upon 1 minus r plus r square into 1 plus r square. Now what we'll do is we'll split this term using partial fraction, and we'll introduce a minus sign. So we can write this as tr, and this is 1 by 2, and here will be 1 upon 1 minus r plus r square minus 1 upon 1 plus r square. Now here this 1 plus r square will cancel and 2 and 2 will cancel. So we'll get the same term. Now our first term will be 1 by 2, and if we put r as 1, it will be 1 upon 1 minus, and if we put r as 1, it will be 1 by 3. Now the second term will be 1 by 2, and here it is 5 minus 2, 1 by 3 minus, and this is 1 by 7. Now this third term will be 1 by 2, and this is 10 minus 3, 7, and here will be 9 and 4, 13. And we continue up to nth term, which is 1 by 2, 1 upon 1 minus n plus n square minus 1 upon 1 plus n square. Now if we add all these terms, we'll get sum of first n terms. So Sn is basically sum of t1 plus t2 up to tn. Now if we add them, these successive terms, they'll cancel, and what we're left with is this first term and last term. So this Sn will be 1 by 2 and then 1 minus 1 upon n square plus n plus 1, or simply n square plus n upon 2 into n square plus n plus 1. And that is the answer to this question. Now let us take another question, and here the question is we need to find sum of first 10 terms of this series. Now what we'll do is, rather than finding sum of first 10 terms, we'll find sum of first n terms. Now we can have this series as 7 upon 2 square into 5 square plus 13 upon 5 square into 8 square plus 19 upon 8 square into 11 square up to n terms. Now we can write this series S as, now 7 is 2 plus 5, so it will be 2 plus 5 upon 2 square into 5 square. 13 is 5 plus 8, so it will be 5 plus 8 upon 5 square, 8 square. This is 8 plus 11 upon 8 square into 11 square up to n terms. Now if we look at these first terms in the denominator, 2, 5, 8, it is an AP. So we'll find nth term of this AP or rth term. So it will be a plus r minus 1 into common difference, which is 3. So there will be 3r minus 1. So we can write its general term tr as 3r minus 1 whole square. Now this next term is 3 more than the first term. So there will be 3r minus 1 plus 3. So there will be 3r plus 2 whole square. And the numerator, it is simply the addition of these two terms. So it is 3r minus 1 plus 3r plus 2. Now since we have to solve this question, we need to use method of difference and we have to introduce a minus sign. So what we'll do is we'll multiply and divide it with 3r plus 2 minus 3r minus 1, and which essentially is 3. So we'll multiply and divide it with 3. Now this is a plus b into a minus b. So we can write 1 by 3, and this is 3r plus 2 whole square minus 3r minus 1 whole square upon 3r minus 1 whole square into 3r plus 2 whole square. Now we'll split this. We can write this as tr equals 1 by 3. Here 3r plus 2 square will cancel, so we'll get 1 upon 3r minus 1 square minus, and here 3r minus 1 will cancel, we'll get 1 upon 3r plus 2 whole square. Now we'll write its first term t1, it will be 1 by 3, and if we put r as 1, we'll get this as 1 upon 2 square minus, and it will be 1 upon 5 square. For second term, we'll put r as 2, so there will be t2 equals 1 by 3, and it is 1 upon 5 square minus 1 upon 8 square. Third term will be 1 by 3, 1 upon 8 square minus 1 upon 11 square, and we'll go on, and its nth term will be tn equals 1 by 3, 1 upon 3n minus 1 whole square minus 3n plus 2 whole square. Now we add them. Now Sn is sum of these n terms. So if we add all these terms, we'll get Sn. Now here 5 square will cancel, 8 square will cancel, 11 square will cancel. Now here we have 1 upon 2 square. So what remains is 1 upon 3n plus 2 square. So it will be 1 by 3, 1 upon 2 square minus 1 upon 3n plus 2 square. And that is solve this series up to n terms. Now in this question, what they have asked for is sum of n terms. So we'll put n as 10. So it will be 1 by 3. And this is 1 by 4 minus, and this is 1 by 30 plus 2, 32 square, which is 1024. Now this is 1 by 3. And denominator will be 1024. And here will be 256 minus 1, 255. If we divide it with 3, there will be 85 upon 1024. So answer to this question is 85 upon 1024, which is your option B. Now here the question is, we need to find sum of n terms of this series, which is given as this summation. R varies from 1 to 10. We'll find it for general term n. From 1 to n, r upon 1 minus 3r square plus r to the power 4. Now this again is similar to the question which you have done previously. Now r varies from 1 to n. This is r, and what we'll do is we'll write this is 1 minus 2r square plus r to the power 4 minus r square, which is this summation r upon r square minus 1 whole square minus r square, which is this summation r upon, now this is a plus b into a minus b, so it will be r square minus r minus 1 into r square plus r minus 1, and that's your r term. Now we can use partial fraction. We can write this as 1 by 2, and it is 1 upon r square minus r minus 1, and this is minus 1 upon r square plus r minus 1. Now here r square will cancel, 1 will cancel, we'll get this as 2r, and this 2 will also cancel, so we'll get the same term. Now this first term is 1 by 2 minus 1 minus plus 1. Second term is 1 by 2. Now this is 4 minus 3, 1. And if we put r as 2, there will be 4 plus 2, 6 minus 1. So it will be 1 by 5. For r equals 3, it will be 1 by 2. And then it will be 9. 9 minus 4, 1 by 5 minus. And here it will be 9 plus 3, 12 minus 1, 11. And its nth term will be 1 by 2, 1 upon n square minus n minus 1 upon 1 upon n square plus n minus 1. Now if we add all these terms, we'll get our Sn. So this Sn, it will be these terms, they'll cancel. 1 by 2, and this is minus 1 minus 1 upon n square plus n minus 1. Now we need to find the sum of 10 terms. So we'll put n as 10. So it will be this minus 1 minus 1 upon, and this is 100, 110 minus 1. So it will be 109. So it is minus 110 upon 2 into 109, which is minus 55 upon 109. And that's your option D. Now here the question is, we need to find the value of this summation. N varies from 3 to infinite, 1 upon n to the power 5 minus 5n cube plus 4n. So its general term or its nth term will be 1 upon, we'll take n common, and that will be n to the power 4 minus 5n square plus 4, which we can also write as n, and this is n square minus 1 and n square minus 4. Now this is a plus b into a minus b, so we can write its general term as 1 upon n minus 2, n minus 1, n plus 1, n plus 2. Now difference between these two terms is 4. So what we'll do is we'll multiply with 4 and we'll divided with 4. So we can write its general term or its rth term as 1 by 4, and here it will be this r plus 2 minus r minus 2 upon r minus 2, r minus 1, r plus 1, r plus 2, and we'll split it in two parts. So we'll write this rth term as 1 by 4. Now here r plus 2 will cancel, so we'll get 1 upon r minus 2, r minus 1, r plus 1 minus 1 upon, and here it will be r minus 1, r plus 1, r plus 2. Now this summation, it starts from r equals 3. So this first term, suppose it is t1 dash, will be 1 by 4, and if we put r as 3, we'll get this as 1, 2, 3, 4, and here it will be 2, 3, 4, 5. And the second term will be 1 by 4. This is 2, 3, 4, 5 minus 3, 4, 5, 6. I'll continue up to n terms. So there will be 1 by 4, and this is n minus 2, n minus 1, n plus 1 minus 1 upon n minus 1, n plus 1, n plus 2. Now if we add them all up, all these terms, they'll cancel. So sum of n terms for this series, it will be 1 by 4, and this is 1 by 24 minus 1 upon n minus 1, n plus 1 into n plus 2. So that is sum of n terms. Now if we find this sum up to infinite, so it will be limit n tends to infinite Sn, and there will be 1 by 4 into 1 by 24 minus, and this is 0, so it will be 1 by 96, and that's your option B. Now here the question is, we need to find the value of this series, which is this summation r varies from 1 to infinite, and this is 4r plus 5 into 5 to the power minus r upon r into 5r plus 5, and that's your S infinite. Now what we'll do is, we'll first find sum up to n terms. We'll write its general term, it will be 4r plus 5 into 5 to the power minus r upon r, and this is 5r plus 5. Now we can write this as 5r plus 5 minus r into 5 to the power minus r upon r into 5r plus 5. Now we'll split it in two parts. Now for this first one, 5r plus 5 will cancel, so we get 5 to the power minus r upon r minus, and here r will cancel, and if we take 5 common, there will be 5 to the power minus r minus 1 upon r plus 1, and that's your rth term. Now this first term will be 5 to the power minus 1 upon 1, and this is 5 to the power minus 2 upon 2. Its second term will be 5 to the power minus 2 upon 2 minus 5 to the power minus 3 upon 3, and it will continue up to its nth term, which is 5 to the power minus n upon n minus 5 to the power minus n minus 1 upon n plus 1. Now if we add them, we'll get sum of n terms. Now these terms, they'll cancel, so sum of n terms will be simply 5 to the power minus 1 minus 5 to the power minus n minus 1 upon n plus 1, and that is the sum of first n terms. Now in this question, we need to find S infinite. So S infinite, which is simply S, will be this limit n tends to infinite Sn, Now this is 1 by 5 and then minus. Now 5 to the power minus infinite is 0 and this is infinite. So this expression will be 0. So value of s is simply 1 by 5. And that's your option A. Now here the question is, our term of series can be written as AR equals FR minus 1 and Sn is summation AR, which is Fn minus F0, and S infinite is limit n tends to infinite Sn. Now first we need to find value of this summation. R varies from 1 to infinite 4r minus 1 pi to the power r upon r square plus r. What we'll do is, we can write this as this summation r varies from 1 to infinite. Now we can write this as 5r minus r plus 1 upon r into r plus 1 into 5 to the power r, and will be this summation r varies from 1 to infinite. Now we multiply them, this r and r will cancel, we get 5 to the power r plus 1 upon r plus 1 minus, now here r plus 1 will cancel, we get 5 to the power r upon r. Now if we put r as 1, we get this as 5 square upon 2 minus 5 upon 1 plus 5 cube upon 3 minus 5 square upon 2 up to infinite. Now these successive terms, they'll cancel, but the problem here is we have this GP whose common ratio is 5, which is greater than 1. So this series is not going to converge. So even though the terms are cancelling, we have this telescopic summation, but this telescopic summation, it doesn't converge. Now proper way to solve this question would have been, rather than finding sum to infinite, we'll find sum of n terms. Now sum of n terms will be 5 square by 2 minus 5 upon 1 plus 5 cube by 3 minus 5 square upon 2 up to 5 to the power n plus 1 upon n plus 1 minus 5 to the power n upon n. Now these terms, they'll cancel. So in the end, we'll have this Sn as 5 to the power n plus 1 upon n plus 1 minus 5. Now if we take this limit n tends to infinite, Sn will be this limit n tends to infinite 5 to the power n plus 1 upon n plus 1 minus 5. Now this is infinity upon infinity form. We can use L'Hopital's rule. So we can write this limit n tends to infinite Sn, it will be this limit n tends to infinite 5 to the power n plus 1 ln 5 upon 1 minus 5. Now 5 to the power infinite is infinite. So this series, it doesn't converge. So we do not have a limiting value of sum. So answer to this first question is this option D, none of these. Now for this second question, we are given that cos 1 minus 1 summation sine n, where n varies from 1 to 50 plus sine 1 summation cos n, n varies from 1 to 50. Now we'll rearrange it a bit. We'll take these terms together. So we can write this as this summation n varies from 1 to 50 cos 1 sine n plus sine 1 cos n, and minus this summation n varies from 1 to 50 sine n. Now this is sine a cos b plus cos a sine b, sine a plus b. So we can write this as this summation n varies from 1 to 50, and this is sine n plus 1, and this is minus sine n. Now you put n as 1, it will be sine 2 minus sine 1 plus sine 3 minus sine 2, and we'll go all the way up to sine 51 minus sine 50. Now these successive terms will cancel. So we'll get this result as sine 51 degrees minus sine 1 degrees, and that's your option C. So answer to the second question is this option C. And then we have this third question where it is 3 into factorial 3 plus 4 into factorial 4 up to 50 terms. Now its general term will be r plus 2 into factorial r plus 2, where r varies from 1 to 50. Now we can write this as r plus 3 minus 1 factorial r plus 2. R plus 3 into factorial r plus 2 is factorial r plus 3 and minus factorial r plus 2. Now we write Sn. Now when r is 1, this is factorial 4 minus factorial 3, then it will be factorial 5 minus factorial 4, and in the end we'll have factorial 53 minus factorial 52. All these successive terms will cancel. So we'll get this as factorial 53 minus factorial 3, or this is factorial 53 minus 6. Now they have expressed it in the form factorial a minus b. So this a is 53 and b is 6. Now we need to find the value of a minus b. Now 53 minus 6 is 47, which is your option C. Now the question is, we are given this series S, which is under root of 1 plus 1 upon 1 square plus 1 upon 2 square plus under root 1 plus 1 upon 2 square plus 1 upon 3 square up to under root of 1 plus 1 upon 199 square plus 1 upon 2000 square. Then we need to find the value of mod of 2000 into S minus 2000. Now if we write its general term, its TRth term will be under root of 1 plus 1 upon r square plus 1 upon r plus 1 square. We can write this as under root of r square, r plus 1 square plus r plus 1 square plus r square upon r square into r plus 1 square. We want to simplify this. We can write this as r to the power 4 plus r square plus 2r cube plus r square plus 1 plus 2r plus r square upon r square into r plus 1 whole square. Now it is under root of r to the power 4 plus 2r cube plus 3r square plus 2r plus 1 upon r square into r plus 1 whole square. Now if we divide everything with r square, we can write this as r square, and we'll take this 1, so it will be 1 upon r square plus, now this is 2r, and here will be plus 2 upon r plus 3 and upon r plus 1 square. Now what we'll do is we'll add 2 and we'll subtract 2, so we can write this as under root of, now this is r plus 1 upon r whole square plus 2 r plus 1 upon r plus 1 upon r plus 1 whole square. Now this is nothing but a square plus b square plus 2ab, which is a plus b whole square. So it will be this under root of r plus 1 upon r plus 1 whole square upon r plus 1 square. So it will be simply r square plus r plus 1 upon r into r plus 1. Now we can write this tr as 1 plus 1 upon r minus 1 upon r plus 1. So we have simplified this term as 1 plus 1 upon r minus 1 upon r plus 1. Now we need to find sum of first 1999 terms. We need to find sum of first 1999 terms. So we write T1. So it will be 1 plus 1 upon 1 minus 1 upon 2. T2 it will be 1 plus 1 upon 2 minus 1 upon 3. And T1999 it will be 1 plus 1 upon 1999 minus 1 upon 2000. Now if we add them all up, we'll get this resulting sum which we need, which is S. Now this is 1 plus 1 plus 1, 1999 times. So that is 1999. Now all these terms, they'll cancel. Here we get 1 minus 1 upon 2000. So this is S minus 2000. It is equal to minus 1 upon 2000. And we cross multiply and take mod. We can write mod of 2000 into S minus 2000. It is equal to 1. So answer to this question is simply 1. Now the question is, the inverse of sum of the following series up to n terms can be. Now basically, I think we need the sum of the following series up to n terms. So we given this series which is 3 by 4, 5 by 36, 7 by 144 up to n terms. Now this is 2 square. This is 2 square into 3 square. This is 3 square into 4 square. So its general term will be 2r plus 1 upon r square into r plus 1 square, which we can write as 1 upon r square minus 1 upon r plus 1 whole square. Now sum of n terms will be this first term plus this second term and then this nth term. Now if we add them all up, we'll get this sum as 1 minus 1 upon n plus 1 square. Now this is n plus 1 square minus 1 upon n plus 1 square. Now this is n square plus 2n upon n plus 1 whole square, and that's your sum, and that's your option 3. Now here the question is, we need to find sum of this infinite series which is 1 by 9 plus 1 by 18, 1 by 30, 1 by 45, 1 by 63 up to infinite. Now we can take 1 by 3 common. So it will be this 1 by 3, 1 by 6, 1 by 10, 1 by 15, 1 by 21. Now this is 1 by 3 and this is 1 into 3. This is 3 into 2. This is 5 into 2. This is 5 into 3. This is 7 into 3. Now what we can see is, here we have 1, 3, 3, 2, 5, 2. So we can write this as 2, 3, 3, 4, 4, 5, 5, 6, 6, 7. So we'll multiply by 2 and divide by 2. So we'll write 2 by 3. And this is 1 upon 2 into 3. 1 upon 3 into 4, 1 upon 4 into 5, 1 upon 5 into 6 up to infinite. So it will be this 2 by 3, and this is 1 by 2 minus 1 by 3, 1 by 3 minus 1 by 4, and this series it continues up to infinite. So answer to this series is simply 1 by 3, and that's your option A. Now here the question is, if S1, S2, S3, Sn are sum of infinite geometric series whose first terms are 1, 3, 5, 2n minus 1, and common ratios are 2 by 3, 2 by 5, and 2 upon 2n plus 1, then find the sum of the series up to infinite terms. Now what we'll do is, we'll take this general series, suppose Sk. Now for this Sk, first term Ak, it is given by 2k minus 1, and its common ratio will be 2 upon 2k plus 1. Now since this is sum of an infinite GP, Sk is Ak upon 1 minus R, so it is 2k minus 1 upon 1 minus 2 upon 2k plus 1. Now here will be 2k minus 1, 2k plus 1, and will be 2k minus 1. So this Sk is nothing but it is 2k plus 1. So if we look at sum of the series S, it is 1 upon S1, S2, S3 plus 1 upon S2, S3, S4, S3, S4, S5, and it continues up to infinite. Now S1 is 3, so it is 3 into 5 into 7. This is 5 into 7 into 9, 7 into 9 into 11. Now here the terms, they are in AP, and the difference between the first and last term in each expression is 4. So this difference, it is 4. So what we'll do is, we'll multiply with 4 and we'll divide with 4. Now we can write this as 7 minus 3, and this is 3 into 5 into 7. This is 9 minus 5, 5 into 7 into 9, 11 minus 7, 7 into 9 into 11. This is 1 by 4. Now here we have to split it. This 7 is going to cancel, so it will be 1 upon 3 into 5 minus 1 upon 5 into 7 plus, here 9 will cancel, so it will be 1 upon 5 into 7 minus 1 upon 7 into 9 plus 1 upon 7 into 9, and it goes on. All these successive terms, they will cancel. So answer to this series is 1 upon 3 into 4 into 5, which is 1 by 60. So answer to this question is 1 by 60, and that's your option B. Now here the question is, let A1 equals 0 and A1, A2, A3, An be real numbers such that mod of Ai equals mod of I minus 1 plus 1 for all I, then arithmetic mean of these numbers has a value A, where which of the following is or are true. Now we square these, we can write Ai square will be equal to Ai minus 1 square plus 1 plus 2 Ai minus 1, or we can write Ai square minus Ai minus 1 square, it is equal to 1 plus 2 Ai minus 1. Now for this A, what we'll need is, we'll need A1 plus A2 up to An. So what we'll do is, we'll start from An plus 1 square minus An square, and it will be equal to 1 plus 2An. Then we can write An square minus An minus 1 square will be 1 plus 2 An minus 1, and we'll continue till a2 square minus a1 square, and it will be equal to 1 plus 2a1. Now, if we add all these successive terms, they'll cancel. And we know that a1 is 0. So this value will be 0. So from here we can write a square n plus 1. It will be 1 plus 1 plus 1 n times. So there will be simply n plus 2 times a1 plus a2 up to an, and we know that square of any number is simply greater than or equal to 0. Now if we divide everything with n, we can write 1 plus 2 into a1 plus a2 plus an by n, that is greater than or equal to 0. This is nothing but arithmetic mean of these values a. So we'll get 1 plus 2a is greater than or equal to 0, or a is simply greater than or equal to minus 1 by 2, and that's your option C. Now here the question is, we need to find value of this summation. So we write its general term TR, it is 1 upon under root of a plus rx plus under root of a plus r minus 1x. Now what we'll do is, we'll rationalize it. So we can write under root of a plus rx minus under root of a plus r minus 1x upon, this is a plus b into a minus b. So there will be a square minus b square. So we can write a plus rx minus a plus r minus 1x. Now a will cancel and rx will also cancel. So it will be simply under root of a plus rx minus under root of a plus r minus 1x upon x. Now we need to find this sum, which is summation r varies from 1 to n TR. Now we put r as 1, it will be under root of a plus x minus under root of a plus under root of a plus 2x minus under root of a plus x, and we'll continue up to under root of a plus nx minus under root of a plus n minus 1x, and we have this x for all the terms. Now all these successive terms, they'll cancel. So we'll have this sum as under root of a plus nx minus under root of a whole divided by x. So the correct option is this option B. Now here the question is, if h1, h2, h3, h2n plus 1 are in HP, then we need to find value of this sum, which is this summation I varies from 1 to 2n minus 1 to the power I hi plus h I plus 1 upon hi minus h I plus 1. Now what we'll do is, we'll divide numerator and denominator with hi plus 1. So we can write this summation as summation I varies from 1 to 2n 1 upon hi plus 1 plus 1 upon hi, and we have minus 1 to the power I upon 1 upon hi plus 1 minus 1 upon hi. Now we know that if h1, h2, h3, hn are in HP, then 1 upon h1, 1 upon h2 and 1 upon h2n plus 1 will be an AP, and suppose its common difference is D. So in the denominator, it is nothing but it is D. So we can write this sum as 1 by D, and then this summation I varies from 1 to 2n minus 1 to the power I 1 upon h I plus 1 plus 1 upon hi. Now we'll expand it. If we put I as 1, we get minus 1 upon h2 minus 1 upon h1. And then for I equals to, it will be plus. So it will be 1 upon h3 plus 1 upon h2 and then minus 1 upon h4 minus 1 upon h3, and in the end we'll have plus 1 upon h2n plus 1 plus 1 upon h2n. Now h2 will cancel, h3 will cancel, all these successive terms they'll cancel. So we'll get the series as S equals 1 by d 1 upon h2n plus 1 minus 1 upon h1. Now this is 2n plus 1th term of an AP. So it will be 1 by d 1 upon h1 plus 2nd minus 1 upon h1. Now h1 will cancel, d will also cancel. So this sum will be equal to 2n. So answer to this question is 2n, and that's your option C. Now here the question is, we need to find sum of this infinite series which is given by this summation r varies from 1 to infinite r cube plus r square plus 1 whole square upon r to the power 4 plus r square plus 1 into r plus 1. What we will do is, first we'll simplify this general term which is say tr. Now this tr will be r cube plus r to the power 4 plus 2r square plus 1 upon r to the power 4 plus r square plus 1 into r plus 1. Now in the numerator, we'll rearrange it a bit. So we can write r to the power 4 plus r square plus 1 and plus r cube plus r square will divide by r to the power 4 plus r square plus 1 into r plus 1. Now we'll split this. So we can write tr here, r to the power 4 r square plus 1 will cancel. So we get 1 upon r into r plus 1, and here r into r plus 1 will cancel. So we get r upon r to the power 4 plus r square plus 1. Now here we'll add r square and we'll subtract r square, and also we multiply and divide it with 2. So we can write this tr as 1 upon r minus 1 upon r plus 1 plus 1 by 2 2r, and this is r square plus 1 whole square minus r square, a plus b, a minus b. So it will be r square plus r plus 1 into r square minus r plus 1. Now we can write this as 1 upon r minus 1 upon r plus 1 plus 1 by 2, and this is 1 upon r square minus r plus 1 minus 1 upon r square plus r plus 1. So that's a general term. Now it is telescopic summation. So we'll put the values of t. So t1 will 1 minus 1 by 2, and this is 1 by 2 will be 1 minus 1 by 3. For second term, we'll put r as 2, so it will be 1 by 2 minus 1 by 3 plus 1 by 2, and here will be 1 by 3 minus 1 by 7, and we'll continue And since it is an infinite series, all these successive terms, they'll cancel. So sum of all the terms up to infinite will be given by simply 1 plus 1 by 2, which is 3 by 2. So answer to this summation is 3 by 2, and that's your option A. Now here the question is, if n is set of all natural numbers and r is set of all real numbers, then a function f defined from n to r is given by fn equals 4n plus under root of 4n square minus 1 upon under root of 2n minus 1 plus under root of 2n plus 1. Now what we'll do is, we can write this as 2n plus 1 plus 2n minus 1 plus under root of 2n plus 1, 2n minus 1 whole divided by 2n minus 1 plus under root of 2n plus 1. And if we take under root 2n plus 1 as a and under root 2n minus 1 as b, so we have taken let under root 2n plus 1 is a and under root 2n minus 1 is b, then basically this fn, it is a square plus b square plus ab upon a plus b. What we'll do is, we'll multiply and divide it with a minus b. Now this is a minus b into a square plus b square plus ab, so it will be a cube minus b cube, and here it is a square minus b square. Now if we look at a square minus b square, it will be 2n plus 1 minus 2n minus 1. This 2n and 2n will cancel. So in the denominator, we'll have 2. So it will be simply a cube minus b cube by 2. So we can write this fn as 1 by 2, and then it is 2n plus 1 to the power 3 by 2 minus 2n minus 1 to the power 3 by 2. Now we need to find greatest integer function of this summation divided by 40. So first we'll calculate this summation. So we find this summation r varies from 1 to 40 fr. So we'll find this summation r varies from 1 to 40 fr. So it will be this 1 by 2. If we put r as 1, we'll get this as 3 to the power 3 by 2 minus 1 to the power 3 by 2. If we put r as 2, we'll get 5 to the power 3 by 2 minus 3 to the power 3 by 2. And if we put r as 40, it will be 81 to the power 3 by 2 minus 79 to the power 3 by 2. Now these successive terms, they'll cancel. So we'll get this summation as 1 by 2. Now this is 81 to the power 3 by 2. Now this is 9 square. So it will be 9 cube. 9 cube is 729. So it will be 729 minus 1. So it will be 728 divided by 2. And it will be 364. Now we need to find greatest integer function of this summation r varies from 1 to 40 fr upon 40. Its greatest integer value. So it will be 364 upon 40. So this is Grid is your function of 9.1. So this value will be equal to 9. So value of this series, it is equal to 9, and that is the answer to this question. Now here the question is, we have to find solve the series which is in summation form. So we'll write its general term or its kth term is 1 upon sine pi by 4 plus k minus 1 pi by 6 into sine pi by 4 plus k pi by 6. Now difference between these two angles is pi by 6. So what we'll do is we'll multiply and divide everything with sine pi by 6. Now sine pi by 6 is 1 by 2. So this is simply 2. So we can write this tk as 2 times, and we want to write this sine pi by 6 as sine pi by 4 plus k pi by 6 minus pi by 4 plus k minus 1 pi by 6 whole divided by sine pi by 4 plus k minus 1 pi by 6, and this is sine pi by 4 plus k pi by 6. Now this is sin A cos B minus cos A sin B. Now if we split, in the first part sin pi by 4 plus k pi by 6 will cancel. So we'll get this tk as 2 times, and then we'll have cos upon sine. So there will be cot pi by 4 plus k minus 1 pi by 6, and then minus cot. In the second part, this k minus 1 part will cancel. We'll get pi by 4 plus k pi by 6. Now we'll find this sum, which is this summation. K varies from 1 to 13 tk. Now this is nothing but this is a telescopic summation. So if we put k as 1, we get cot pi by 4 minus cot pi by 4 plus pi by 6. If we put k as 2, we get cot pi by 4 plus pi by 6. Then minus will continue, and in the end we'll have minus cot pi by 4 plus pi by 6. Now all these terms, they'll cancel. So value of this summation will be 2 cot pi by 4 minus cot pi by 4 plus 13 pi by 6. Now cot pi by 4 is 1, and 13 pi by 6 is 2 pi plus pi by 6. And after 2 pi, angle is same. So this is cot pi by 4 plus pi by 6. Now this value is 2, and this is 1 minus cot A cot B minus 1. So it will be cot pi by 4 1, and cot pi by 6 is root 3 minus 1 upon 1 plus root 3. So we get this as 4 upon root 3 plus 1, and if we rationalize it, we can write 2 into root 3 minus 1. So answer to this question is 2 into root 3 minus 1, and that's your option C. Now the next question is very standard question. We can write this S and X as this summation tan inverse k plus 1x minus kx upon 1 plus kx into k plus 1x which is this summation tan inverse k plus 1x minus tan inverse of kx. Now we put the value of this summation, then it starts from 1, so it will be tan inverse 2x minus tan inverse x plus tan inverse 3x minus tan inverse 2x, and finally it will go up to tan inverse n plus 1x minus tan inverse nx. Now all these, they'll cancel, so we'll get this s and x as tan inverse n plus 1x minus tan inverse of x, which is tan inverse a minus b. So it will be this nx upon 1 plus a into b. So it will be n plus 1 into x square, and that's your function s n x. Now the first part is we need to find s tan x. Now this s tan x will be tan inverse tan x upon 1 plus 11x square. Now since x is greater than 0, we can write this as cot inverse 1 plus 11x square upon tan x, and we know that cot inverse x is pi by 2 minus tan inverse x, so it will be pi by 2 minus tan inverse 1 plus 11x square upon tan x. So that means this option A, it is correct. Now if we look at this option B, then this cot of this limit n tends to infinite. Now if we take limit n tends to infinite, this limit will be tan inverse of, now coefficient of n, here it is x and here it is x square. Now this x and x will cancel, so we'll get this as cot of tan inverse of 1 by x, and since x is greater than 0, it is nothing but it is cot inverse of x, which is nothing but x. So that means this option B is also correct. Now we look at this S3x. Now it says S3x equals pi by 4 has a root n 0 to infinite. Now S3 is tan inverse 3x upon 1 plus 4x square, and if we take it equal to pi by 4, then we'll get this as 4x square minus 3x plus 1 equals 0. Now for this, if we find D is 9 minus 16, which is less than 0, that means this is always positive. So this equation, it won't have any real root. So that means this option C, it is incorrect. And then finally, this D, which is tan S n x. Now if we look at this tan S n x, now this tan S n x will be nx upon 1 plus n plus 1x square. Now if we take this as y, and if we differentiate this function dy by dx, then it will be equal to 1 minus n plus 1x square into n upon 1 plus n plus 1x square whole square. So here we'll get one root, and which is 1 upon under root of n plus 1. Now this is plus and this is minus. So this function, it will have a local maxima at 1 upon under root n plus 1. Now if we find its value at 1 upon under root n plus 1, this value will be n upon under root of n plus 1 by 2, which is n upon 2 under root n plus 1. Now this is greater than n upon 2 root n, which is under root n by 2. So this value is always greater than 1 by 2, not less than 1 by 2. So that means this option D is incorrect. So the correct options are A and B. Now let us take another problem, and it is this series S is summation R varies from 1 to 90 2r upon 2 plus r square plus r to the power 4. Now again we have to introduce a minus sign. Now here what we'll do is we'll add r square and we'll subtract r square. So we'll write this series as the summation r varies from 1 to 90 and it'll be 2r, and here we'll take this 1 and then 1 plus 2r square plus r to the power 4 minus r square. So we can write this series as this summation r varies from 1 to 90 and it'll be 2r upon 1 plus it'll be r square plus 1 whole square minus r square. Now this is a plus b into a minus b. So we can express this as this summation r varies from 1 to 90 1 plus r square plus r plus 1 into r square minus r plus 1 and it'll be r square plus r plus 1 minus r square minus r plus 1, and we have tan inverse all the way. Now this is tan inverse x minus y upon 1 plus xy. So we can write this as this summation r varies from 1 to 90 tan inverse r square plus r plus 1 minus tan inverse r square minus r plus 1. Now we need to find this summation when r varies from 1 to 90. Suppose this is tr. Now we'll write t1 and t1 will be tan inverse 3 minus tan inverse 1. t2 it will be tan inverse 7 minus tan inverse 3. t3 will be tan inverse 13 minus tan inverse 7, and it'll continue up to t90, which is tan inverse 90 square plus 90 plus 1 minus tan inverse 90 square minus 90 plus 1. Now we'll add them all up, we'll get our Sn. Now here tan inverse 3 will cancel. So in the end, we'll get this sum S90 as tan inverse 8100 plus 90 plus 1 minus tan inverse 1, which is tan inverse 8191 minus tan inverse 1, and it'll be tan inverse 8190 upon 8192. Now we'll take this 10 here, so we'll write 10s equals 8190 upon 8192. Now we need to find the value of 8190 cot s, and it'll be simply 8192. So answer to this question will be 8192, and that is the answer to this question. Now here the problem is we need to find the value of cosec inverse root 5, cosec inverse root 65, cosec inverse root 325, and it goes all the way up to infinite. Now what we'll do is we'll change each of this expression in terms of tan inverse. Now cosec theta is root 5. So this is theta, this is root 5, this is 1, and here this value will be 2. So we'll write this as tan inverse 1 by 2. Now for the second one, we'll have root 65, this is 1, and it'll be root 64, it'll be 8, so it'll be tan inverse 1 by 8. Next one will be 325, 1, and it'll be under root of 324, it'll be tan inverse 1 by 18, and this series will continue up to infinite. Now in this form we do not see any pattern, so actually I'll try and express it as 2 by 4 tan inverse 2 by 16 tan inverse 2 by 36, and we'll write this as 1 plus 1 into 3 tan inverse 1 plus 3 into 5 tan inverse 1 plus 5 into 7, and the series it continues up to infinite. So we can write this series as tan inverse 3 minus 1 upon 1 plus 1 into 3 tan inverse 5 minus 3 upon 1 plus 3 into 5 tan inverse 7 minus 5 upon 1 plus 5 into 7, and so on. So we'll write this as tan inverse 3 minus tan inverse 1 plus tan inverse 5 minus tan inverse 3 tan inverse 7 minus tan inverse 5. It goes all the way up to infinite. Now here 3 will cancel, 5 will cancel. So in the end, loosely speaking, we'll get tan inverse infinite minus tan inverse 1, which is
pi by 2 minus pi by 4, and it is pi by 4. So value of k will be simply 1. Now let us take another question, and it is cot of this summation n varies from 1 to 23 cot inverse 1 plus, and then this summation k varies from 1 to n 2k. Now first we'll simplify this summation. Now we can write this as cot of, and then this summation n varies from 1 to 23 cot inverse 1 plus, we'll take this 2 common, and then summation k. Now summation k is nothing but n plus 1 by 2. So we'll cancel this 2 with 2. So we can write this as cot of summation n varies from 1 to 23 cot inverse of 1 plus n into n plus 1. Now since n is a positive number, we can write cot inverse x as tan inverse 1 by x. So we'll actually write this as cot of, and this summation n varies from 1 to 23 tan inverse 1 upon 1 plus n into n plus 1. Now we have to express it as tan inverse x minus tan inverse y. So what we'll do is we'll actually write this as cot of, then this summation n varies from 1 to 23 tan inverse n plus 1 minus n upon 1 plus n into n plus 1. So it will be nothing but tan inverse x minus y upon 1 plus xy. So we'll write this as cot of, and then this summation n varies from 1 to 23 tan inverse n plus 1 minus tan inverse of n. Now we'll start expanding this summation. So we can write this as cot of, now we'll put n as 1, we'll get tan inverse 2 minus tan inverse 1. For n equals 2, it'll be tan inverse 3 minus tan inverse 2, and it'll continue up to 23, where it will be tan inverse 24 minus tan inverse 23. Now here these terms, they'll cancel out, and then in the end we'll get cot of tan inverse 24 minus tan inverse of 1, which we can write as cot of, now tan inverse x minus y, so it'll be 24 minus 1 upon 1 plus 24, so that'll be 25. Now tan inverse x is cot inverse 1 by x, so we can write this as cot of cot inverse 25 by 23. Now here cot and cot inverse will cancel, so answer to this expression will be simply 25 by 23, and that's your option B.
Again, the question is, we are given this function f and x, which is this summation j varies from 1 to n tan inverse 1 upon 1 plus x plus j and x plus j minus 1. In the numerator, we can write this 1 as x plus j minus x plus j minus 1. So it is tan inverse a minus b upon 1 plus ab, since all x, they are greater than 0. So we can write this as summation tan inverse x plus j minus tan inverse x plus j minus 1. Now if we use telescopic summation, we will get this fn x as tan inverse x plus n minus tan inverse x. So this fn x will be simply tan inverse n upon 1 plus x into n plus x. Now in the question we are given that x belongs to 0 to infinite, so that means we have no information about f0, so we cannot comment anything on options A and B since they contain f0. So you want to discard options A and B. Now for the third option, we have this limit x tends to infinite 10 fnx. Now 10 fnx is n upon 1 plus x n plus x. Now any x we have is in the denominator. So as x approaches infinite, this limit it approaches 0. So it is not equal to 1 by n. That means this option C is incorrect. Now if we look at this option D, it says limit x tends to infinite secant square fnx. Now secant square is 1 plus 10 square, so it will be 1 plus 10 square fnx. Now this is limit x tends to infinite, and this is 1 plus, and 10 square fnx is n square upon 1 plus nx plus x square whole square. Now again x tends to infinite, this second limit will be 0, so answer to this limit will be simply 1. So the only correct option is this option B.
Now the next question is very standard question. We can write this S and X as this summation tan inverse k plus 1x minus kx upon 1 plus kx into k plus 1x, which is this summation tan inverse k plus 1x minus tan inverse of kx. Now we put the value of this summation, then it starts from 1, so it will be tan inverse 2x minus tan inverse x plus tan inverse 3x minus tan inverse 2x, and finally it will go up to tan inverse n plus 1x minus tan inverse nx. Now all these they'll cancel, so we'll get this s and x as tan inverse n plus 1x minus tan inverse of x, which is tan inverse a minus b. So it will be this nx upon 1 plus a into b. So it will be n plus 1 into x square, and that's your function s n x. Now the first part is we need to find s tan x. Now this s tan x will be tan inverse tan x upon 1 plus 11x square. Now since x is greater than 0, we can write this as cot inverse 1 plus 11x square upon 10x, and we know that cot inverse x is pi by 2 minus tan inverse x, so it will be pi by 2 minus tan inverse 1 plus 11x square upon 10x. So that means this option A, it is correct. Now if we look at this option B, then this cot of this limit n tends to infinite. Now if we take limit n tends to infinite, this limit will be tan inverse of, now coefficient of n, here it is x and here it is x square. Now this x and x will cancel, so we'll get this as cot of tan inverse of 1 by x, and since x is greater than 0, it is nothing but it is cot inverse of x, which is nothing but x. So that means this option B is also correct. Now we look at this S3x. Now it says S3x equals pi by 4 has a root n 0 to infinite. Now S3 is tan inverse 3x upon 1 plus 4x square, and if we take it equal to pi by 4, then we'll get this as 4x square minus 3x plus 1 equals 0. Now for this, if we find D is 9 minus 16, which is less than 0. That means this is always positive. So this equation, it won't have any real root. So that means this option C, it is incorrect. And then finally, this D, which is tan S and X. Now if we look at this tan S and X, now this tan S and X will be nx upon 1 plus n plus 1x square. Now if we take this as y, and if we differentiate this function dy by dx, then it will be equal to 1 minus n plus 1x square into n upon 1 plus n plus 1x square whole square. So here we'll get one root, and which is 1 upon under root of n plus 1. Now this is plus and this is minus. So this function, it will have a local maximum at 1 upon under root n plus 1. Now if we find its value at 1 upon under root n plus 1, this value will be n upon under root of n plus 1 by 2, which is n upon 2 under root n plus 1. Now this is greater than n upon 2 root n, which is under root n by 2. So this value is always greater than 1 by 2, not less than 1 by 2. So that means this option D is incorrect. So the correct options are A and B. Now in this question we are given an AP with first term 7 and common difference of 8. And T1, T2, T3 be such that T1 equals 3 and Tn plus 1 minus Tn is An, then which of the following is or are true? Now we are given that Tn plus 1 minus Tn, it is equal to An. Now Tn minus 1, it will be An minus 1, and the same way T2 minus T1, it will be equal to A1. Now if we add them all, then all these terms they'll cancel. So from here we'll get Tn plus 1 minus T1, it will be equal to this series, which is A1 plus A2 up to An, which is nothing but sum of first n terms of this AP. Now this is Tn plus 1 minus T1. Now T1 is simply 3. And sum of n terms of this AP will be n by 2, 2a. And 2a is 2 into 7 plus n minus 1 into common difference of 8. Now this is 2 and this is 4. So this Tn plus 1 will be 3 plus n into 7 plus 4n minus 4. So basically this Tn plus 1, it will be 4n square plus 3n plus 3. Now first we'll find the value of T20 and T30. Now if we put n as 19, we'll get 4 into 19 square plus 3 into 19 plus 3. Now this value is 1504. That means this option A is incorrect. And for T30, we'll put n as 29. So it'll be this 4 into 29 square plus 3 into 29 plus 3. And this value is 3454. That means this option C is correct. Now we have to find this summation. K varies from 1 to 20 and 1 to 30. So we have to simplify this summation. K varies from 1 to, suppose, capital N Tk, which is T1 plus T2 plus Tn. Now we can also write this as this summation. K varies from 0 to n minus 1 T K plus 1, because again will be T1 plus T2 up to Tn. Now this is summation. K varies from 0 to n minus 1, and this is 4k square plus 3k plus 3. So this is 4, and summation k square is n plus 1 to n plus 1 by 6. Here we are dealing with n minus 1, and 3, and n again is n minus 1, n divided by 2, n plus 3, and here this value, it will be n. Now first we'll find this summation. K varies from 1 to 20 Tk. Now here value of n is 20. So if we put n is 20, so it will be this 4 into 19 into 20 into 39 by 6 plus 3 into 19 into 20 divided by 2 plus 3 into 20. And this value is 10510. And summation
K varies from 1 to 30 tk. Now here we'll put n as 30, so it will be this 4 into 29 into 30 into 59 divided by 6, 3, 29 into 30 divided by 2 plus 3 into 30, and this value is 35615. So it is 10510. This is correct, and 35615. That means option D is incorrect. So the correct options are B and C. Now here the question is, let A and be a sequence such that A0 is equal to A1 and it is equal to 0, and we are given this recurring relation which is AN plus 2, it is equal to 3 times AN plus 1 minus 2AN plus 1. Then we need to find A25 into A23 minus 2 times A25 into A22 minus 2 times A23 into A24 plus 4 times A22 into A24. Now here what we'll do is we'll take A25 common and A24 common. So here will be A25 and we'll get A23 minus 2 times A22, and here we'll take minus 2 A24 and we'll get A23 minus 2 A22. So basically we'll need to find this value which is A25 minus 2 A24 into A23 minus 2 A22. So if we can find AN minus 2 AN minus 1, we'll get our result. So now we'll come to this given relation. So we are given that AN plus 2 is 3 times AN plus 1 minus 2 AN plus 1. Now we can take one of the AN plus 1 on the left hand side. We can write AN plus 2 minus AN plus 1 will be equal to 2 times AN plus 1 minus AN plus 1. Now if we replace N with N minus 1, we can write AN plus 1 minus AN will be equal to 2 times AN minus 1 plus 1, and we'll continue. And in the end, we'll have A2 minus A1 will be equal to 2 times A1 minus A0 plus 1. Now, if we add them all, these successive terms, they'll cancel. Here also, these terms, they'll cancel. And we also know value of A1 is 0 and A0 is 0. So from here, we can write AN plus 2, it is equal to 2 times AN plus 1 plus, now this is 1 plus 1 plus 1. Now from 1, it has gone to N plus 1. So there will be total N plus 1 terms. So from here we can say AN plus 2 minus 2 AN plus 1, it is equal to N plus 1. Or if we take N as N minus 2, we can write this as AN minus 2 AN minus 1 will be N minus 1. Now here we have A25 minus A24. Here the value of N is 25. So 25 minus 1 is 24. And A23 minus 2 A22. N is 23. So it will be this 22. So value of this result is 24 into 22, which is 528. So value of this expression, it will be 528, and that is the answer to this question. Now here we are given the sequence A1, A2, A3 such that A1 is equal to 1, A2 is equal to 2, and AN plus 2, it is equal to 2 upon AN plus 1 plus AN, and we need to find value of A1 plus 1 upon A2 upon A3, A2 plus 1 upon A3 upon A4 up to A30 plus 1 upon A31 upon A32. And if this is equal to 2 to the power alpha, 61C31, then we need to find the value of alpha. So first we'll look at what we need to prove. We need to prove A1, A2 plus 1 upon A2, A3 into A2, A3 plus 1 upon A3, A4 and A30 into A31 plus 1 upon A31 into A32. This is equal to sum 2 to the power alpha 61C31. Now since we have A1, A2, A2, A3, so we need product of an and an minus 1. So what we'll do is we'll cross multiply and we'll rearrange this as an plus 2 into an plus 1 minus an plus 1 into an, and it will be equal to 2. Now here we'll replace n with n minus 1. So we can write an plus 1 into an minus an into an minus 1 will be equal to 2. And we'll continue. And in the end we'll have a3 a2 minus a2 a1 and it'll be equal to 2. Now if we add them all up, all these successive terms, they'll cancel. So we'll get an plus 2 into an plus 1 minus a1 into a2 is 2. And this is 2 plus 2 plus 2. Now it goes from 1 to n. So there'll be 2n. So simply an plus 2 into an plus 1 will be 2 times n plus 1, or if we write an into an minus 1, so we'll replace n with n minus 2, so it will be this 2 times n minus 1, and this is the result which we are going to use to find the value of alpha. Now if we look at this left hand side, we can write this left hand side as this product ak into ak plus 1 upon ak plus 1 into ak plus 2, where the value of k, it varies from 1 to 30. Now ak into ak plus 1. So if you put n as k plus 1, we'll get ak plus 1 into ak and will be equal to 2k, and ak plus 1 into ak plus 2 will be 2k plus 1. So we can write this as this product k varies from 1 to 30 and it will be this 2k plus 1 upon 2 into k plus 1. Now if we expand this product, if we put k as 1, we'll get this as 3, 5, 7. I'll go all the way up to 61. And in the denominator, we'll have this 2 30 times. So that'll be 2 to the power 30. And then we'll have k plus 1. So it'll be this 2 into 3 up to 31. Now since we need 61C31, so what we'll do is we'll multiply numerator and denominator with the missing numbers. So we'll multiply 2, 4, 6 up to 60, and in the denominator will be 2 to the power 30. This is 2, 3, 31, and here will be 2, 4, 6, 60. Now in the numerator we'll have 2, 3, 4, 5 up to 61. So numerator will be factorial 61. Now this is 2 to the power 30. This is 2, 3, 4 into 31. And here if we take 2 out from each of these 30 terms, so we'll get 2 to the power 30. And then we'll have 1, 2, 3 up to 30. So it'll be this factorial 61 divided by 2 to the power 60. And this is factorial 31 by factorial 30. So it'll be this 2 to the power minus 60, 61C, 31. So this result, it is equal to 2 to the power minus 60, 61, C31. So that means value of alpha is minus 60. So for this question, value of alpha is minus 60. Now here the question is, we have this sequence where A0 is equal to A1 and it is 0. And we are given that AN plus 2 is equal to 2 times AN plus 1 minus AN plus 1. Then we need to find the summation. N varies from 2 to infinite, AN upon 7 to the power n. Now what we'll do is, we can write this recurring relation as AN plus 2 minus AN plus 1 and it will be equal to AN plus 1 minus AN plus 1. Now, if we put n as n minus 1, we can write AN plus 1 minus AN. It will be equal to AN minus AN minus 1 plus 1. And will continue up to A2 minus A1. And this is equal to A1 minus A0 plus 1. Now, if we add them all up, these terms, they'll cancel. Now, A1 is 0 and A0 is also 0. So we can write AN plus 2. It is equal to AN plus 1 and plus, now this is 1 plus 1 plus 1. Now this starts from 1 to n plus 1. So it will be this n plus 1. So from here we can write AN plus 2 minus AN plus 1 will be equal to n plus 1. So we have another recurring relation. Now from this recurring relation we can write AN plus 2 minus AN plus 1. This is n plus 1. AN plus 1 minus AN will be this n. And it'll go up to A1 minus A naught. It'll be this 0. If we again add them all up, so we'll get this result as AN plus 2, A1 is 0. And this is 1 plus 2 plus 3 up to n plus 1. So this is sum of first n plus 1 numbers. So it'll be this n plus 1, n plus 2 by 2. Or simply we can write AN, it will be n into n minus 1 by 2. So we have our AN as n into n minus 1 by 2. Now we need to find sum of this series, which is this summation. N varies from 2 to infinite, AN by 7 to the power n, which is this summation. N varies from 2 to infinite, and this is n minus 1 by 2 into 1 by 7 to the power n. Now we know that 1 plus x square up to infinite, this is 1 upon 1 minus x when x is less than 1. So basically this is this summation x to the power n, where n varies from 0 to infinite, and this is 1 upon 1 minus x. Now we differentiate this, we can write this summation nx n minus 1 and it'll be equal to minus 1 upon 1 minus x square into minus 1. So there'll be 1 upon 1 minus x square, where n varies from 1 to infinite. And if we differentiate this again, we can write this summation n minus 1 x to the power n minus 2 will be equal to this minus 2 minus 1. So there'll be 2 upon 1 minus x cube. Now we need n minus 1 by 2 into x to the power n. So we'll multiply x square. So we can write n minus 1 we'll divide by 2 and we'll multiply x square. So there'll be x to the power n. So it'll be this x square upon 1 minus x cube, where n varies from 2 to infinite, which is the series that we need. Now here the value of x is 1 by 7. So it'll be this 1 by 7 square upon 1 minus 1 by 7 cube. So there'll be 1 upon 7 square, and this is 6 cube by 7 cube. So there'll be 7 upon 216. So answer to this question is 7 upon 216. Now here the question is, we need to find the sum of this series, which is 1 to the power 4 upon 1 into 3 plus 2 to the power 4 upon 3 to the power 5 up to n to the power 4 upon 2n minus 1 into 2n plus 1. So we can write this series as this summation r varies from 1 to n r to the power 4 upon 2r minus 1 into 2r plus 1. What we'll do is we'll multiply and divide everything with 16 and then we'll add 1 and subtract 1. So we can write this as 1 by 16 and this is summation r varies from 1 to n. Now this is 2r to the power 4 minus 1. So it'll be 2r square whole square minus 1, a plus b into a minus b. So we can write 2r square plus 1 into 2r square minus 1 upon, and this is 2r square minus 1 plus 1 by 16 into this summation r varies from 1 to n 1 upon 2r minus 1 and 2r plus 1. Now here 2r square minus 1 will cancel. So we'll get this as 1 by 16 is summation 4r square plus 1 plus 1 by 16 and this summation 1 upon 2r minus 1 into 2r plus 1 where r varies from 1 to n. Now this is 1 by 4 summation r square. Now this is 1 by 16 summation 1. So that will be simply n by 16 and plus 1 by 16. Now here we multiply and divide it with 2. So we can write this summation r varies from 1 to n 2 upon 2r minus 1 and 2r plus 1. Now this is 1 by 4 and summation r square is n plus 1 2n plus 1 by 6. This is n by 16 and this is 1 by 32. And we can write this as this summation r varies from 1 to n and this is 1 upon 2r minus 1 minus 1 upon 2r plus 1. Now we can solve this using telescopic summation. So we'll get this as n plus 1 to n plus 1 by 24. This is n by 16 plus 1 by 32 and here we'll have 1 minus and the last term will be 2n plus 1. So it will be this n plus 1 2n plus 1 by 24 plus n by 16 1 by 32 and this is 2n plus 1 minus 1. So there will be 2n upon 2n plus 1. Now 2 and 2 will cancel. Here we'll take n by 16 common. So we can write n plus 1 2n plus 1 divided by 24 plus n by 16 and this is 2n plus 1 plus 1. So there will be 2n plus 2 upon 2n plus 1. We can cancel this 2 also. So we can write this as n plus 1 to n plus 1 by 24 and plus n by 8 into n plus 1 upon 2n plus 1. Now here we can take n plus 1 by 8 common. So if we take n plus 1 by 8 common, we can write 2n plus 1 by 3 plus 1 upon 2n plus 1. If we simplify this, this is 24 into 2n plus 1 and this is n plus 1 and this is 2n plus 1 whole square and plus this is 3 into 1 3. So it will be this n plus 1 and here will be this 4n square plus 4n plus 1 plus 3 4 upon 24 into 2n plus 1. We can cancel this 4. So we'll get this as n plus 1 n square plus n plus 1 upon 6 into 2n plus 1. So answer to this question is, value of the series is n plus 1, n square plus n plus 1 by 6 into 2n plus 1. Now here the question is, we need to find sum of the series a1 upon 1 plus a1 plus a2 upon 1 plus a1 1 plus a2 up to an upon 1 plus a1 1 plus a2 1 plus an. Tn is an upon 1 plus a1 1 plus a2 1 plus an. We'll add 1 and we'll subtract 1. So this tn will be, now here 1 plus an will cancel. So it will be 1 upon 1 plus a1 1 plus a2 1 plus an minus 1 minus 1 upon 1 plus a1 1 plus a2 1 plus an. Now tn minus 1 will be 1 upon 1 plus a1 2 1 plus a n minus 2, and here will be 1 plus a1 1 plus a2 up to 1 plus a n minus 1, and for t1 that will be 1 minus 1 upon 1 plus a1. Now if we add them all up, all these terms they'll cancel. So value of this series will be 1 minus 1 upon 1 plus a1 1 plus a2 up to 1 plus an. Now this we are given an AP. So a1 a2 an, they are an AP with common difference d, which is non-zero. We need to find sum of this series sine d cosec a1 cosec a2 cosec a2 cosec a3 up to cosec an minus 1 into cosec an. Now we'll multiply the sine d inside, so we can write sine d, and we'll also convert them in sine. So we'll write sine a1 sine a2 plus sine d, and this is sine a2 sine a3, and it'll go up to sine d upon sine a n minus 1 sine an. Now we know that common difference, it is equal to a2 minus a1 a3 minus a2 a n minus a n minus 1. So we can write this as sine a2 minus a1 upon sine a1 sine a2. This is sine a3 minus a2 upon sine a2 sine a3. I'll go up to sine an minus an minus 1 upon sine an minus 1 sine an. Now sine a minus b, sine a cos b, cos a sine b. So we can write this as sine a2 cos a1 minus cos a2 sine a1 upon sine a1 sine a2. Now we split them, sine a2 will cancel, so it will be this cot a1 minus, and the second one sine a1 will cancel, so there will be cot a2. So this first one will be cot a1 minus cot a2. Second one will be cot a2 minus cot a3, and here will be cot an minus 1 minus cot an. Now from telescopic summation, all these terms they'll cancel. So sum of the series will be cot a1 minus cot an, and that's your option C.
Now let us take another question, and here we need to find the sum of the series up to infinite terms. What we'll do is we'll find sum up to n terms. Now in the numerator we have the series 2, 6, 12 and 20 and so on. We'll write the differences. 6 minus 2, 4, 12 minus 6, 6, 20 minus 12, 8, Now this is 2 and this is 2. Now we can use the shortcut. This is 2a, this is 3a plus b, and this is a plus b plus c. Now clearly a is 1, and if we put a as 1, we get b as 1, and if we put a and b as 1, we get c as 0. So its nth term will be n square plus n. Now in order to solve this question, we have to write general term of the series. It is TR, and it will be in the numerator we'll have r square plus r. In the first term it is 1 cube, second term it is 1 cube plus 2 cube. So it will be 1 cube plus 2 cube up to r cube. Now we can write this as TR equals r into r plus 1, and this is r plus 1 by 2 whole square. As r plus 1 will cancel, so it will be 4 upon r plus 1, which we can also write as TR equals 4, and this is 1 upon r minus 1 upon r plus 1. Now we need to find sum of n terms. So Sn, it will be 4. Now we put t as 1, it will be 1 upon 1 minus 1 upon 2. If we put t as 2, it will be 1 upon 2 minus 1 upon 3. 1 upon 3 minus 1 upon 4. I will continue up to 1 upon n minus 1 upon n plus 1. Now here 1 by 2, 1 by 3 will cancel. So what we'll get is Sn equals 4 into 1 minus 1 upon n plus 1, which is 4n upon n plus 1. Now we need to find sum up to infinite. Now S infinity is limit n tends to infinite, Sn. Now here highest power of n is 1. So its answer is 4 upon 1, which is simply 4. And that is the answer to this question.
In this video, we'll be proving two very important formulas in trigonometry, and which is sum of the series of sine and cosine when angles are in AP. Now the first formula is sine A plus sine A plus D plus sine A plus 2D up to sine A plus n minus 1D. It is sine n d by 2 upon sine d by 2 into sine A plus n minus 1 d by 2. And in the case of cos A plus cos A plus d plus cos A plus 2d up to cos A plus n minus 1d. It is sine n d by 2 upon sine d by 2 into cos A plus n minus 1d by 2. So between the two formulas, if the series is sine, here we'll have sine, and if the series is in cos, then here we'll have cos. Everything else is just same. Now we'll start proving the formula. We'll prove the formula by two methods, and the first method is using trigonometry. We'll start with this first series, which is sine A plus sine A plus D plus sine A plus 2D, and it goes all the way up to sine A plus n minus 1D. Now what we'll do is we'll multiply and divide everything with 2 sine d by 2. So we can write this as 1 upon 2 sine d by 2, and it'll be 2 sine A into sine d by 2, 2 sine A plus D into sine d by 2, 2 sine A plus 2D into sine d by 2, and it goes on up to 2 sine A plus n minus 1 into D into sine d by 2. Now we know that 2 sine A sine B is cos A minus B minus cos A plus B. So we'll use this formula for each of the term in the expression. Now we can write this as 1 upon 2 sine d by 2. Now cos A minus B. Cos A minus B in this case will be cos A minus d by 2 and minus cos A plus d by 2. Now for the second one, it will be cos a plus d by 2 minus cos a plus 3d by 2. Next one will be cos a plus 3d by 2 minus cos a plus 5d by 2, and in the end we'll have cos a plus n minus 3 by 2d and minus cos a plus n minus 1 by 2d. Now, as you can figure out, this is nothing but method of difference. Here, cos a plus d by 2, cos a plus d by 2 will cancel. A plus 3d by 2, a plus 3d by 2 will cancel. So, all these successive terms, they'll cancel. And in the end, we'll get this as 1 upon 2 sine d by 2, and it'll be cos a minus d by 2 minus cos a plus n minus 1 by 2d. Now here we'll use the formula for cos c minus cos d. Cos c minus cos d is 2 sine c plus d by 2 into sine d minus c by 2. So we can write this as 1 upon 2 sine d by 2, and it'll be 2 sine c plus d by 2. Now we'll add them, we'll get 2a plus n minus 1d whole divided by 2 into sine, now d minus c by 2. Here a minus 1 by 2d will cancel. So we'll get this as sine n d by 2. Now we'll cancel this 2 with 2. We can write this result as sine n d by 2 into sine a plus n minus 1 d by 2 upon sine d by 2, which is the formula that we need to prove. If angles are in AP, then sine A plus sine A plus D plus sine A plus 2D up to sine A plus n minus 1D, which is sum of n terms, it is given by sine n d by 2 upon sine d by 2 into sine A plus n minus 1D by 2. Now in the same way, we'll prove this second formula. So we'll start with cos A plus cos A plus D, and this series will go all the way up to cos A plus n minus 1D. Now again, we'll multiply and divide with 2 sine D by 2. So we can write this as 2 cos A into sine D by 2 plus 2 cos A plus D sine D by 2, and it'll go all the way up to 2 cos A plus n minus 1D into sine D by 2 whole into 1 upon 2 sine D by 2. Now 2 cos A sine B, it is sine A plus B minus sine A minus B. So we'll use the formula. Now we can write this as 1 upon 2 sine D by 2, and this is sine A plus B, which is sine A plus D by 2, and minus sine A minus D by 2. Second one will be sine A plus 3D by 2 minus sine A plus D by 2, and this series will continue, and finally we'll get sine A plus n minus 1 by 2D minus sine A plus n minus 3 by 2D. Now this again is method of difference. Now here sine A plus D by 2 will cancel. So all these successive terms, they'll cancel. In the end, we'll get 1 upon 2 sine D by 2 into sine A plus n minus 1 by 2d minus sine a minus d by 2. Now here we'll use the formula for sine c minus sine d, which is 2 sine c minus d by 2 into cos c plus d by 2. So we'll use the formula. We'll get this as 1 upon 2 sine d by 2, and here it will be 2 sine now a minus b. So here a minus d by 2 will cancel. So we'll get this as n d by 2 into cos now c plus d by 2. So we'll get this as a plus n minus 1 d whole divided by 2. Here 2 and 2 will cancel. So we'll get this as sine n d by 2 upon sine d by 2 into cos a plus n minus 1 d by 2, which is same as the result that we need. Now, second method of proving these two formulas is using complex numbers. So what we'll do is we'll take the sum of the second series as x and the sum of this first series as y. Now we'll find this sum s, which is say x plus iota y. So we can write this as cos a plus iota sine a plus cos a plus d plus iota sine a plus d cos a plus 2d plus iota sine a plus 2d, and it goes all the way up to cos a plus n minus 1d plus iota sine a plus n minus 1 into d. Now here we'll use Euler's formula, and which is cos theta plus iota sine theta. It is nothing but e to the power iota theta. So we can write this as e to the power iota a. We can write the second one as e to the power iota a plus d. This is e to the power iota a plus 2d, and here we'll get e to the power iota a plus n minus 1d. So we can write the series s as e to the power iota a plus e to the power iota a plus d e to the power iota a plus 2d, and it'll go all the way up to e to the power iota a plus n minus 1 into d. Now this is nothing but a GP. So it is a GP of n terms. So we can find this sum using the formula for sum of a GP. So we'll write this sum S as A, which is its first term, e to the power iota a, and then 1 minus r. R in this case is e to the power iota d to the power n upon 1 minus r, which is e to the power iota d. Now we'll try and simplify this. Now this is e to the power iota a, and here we can write this as e to the power iota n d upon 1 minus e to the power iota d. Now again we'll change it in sine and cos. So we can write this as e to the power iota a, and this is 1 minus cos n d minus iota sine n d upon 1 minus cos d minus iota sine d. Now we'll use half angle formulas for cos and sine. So we can write this as e to the power iota a, and here it will be 2 sine square n d by 2, and here we'll write this as 2 iota sine n d by 2 into cos n d by 2, and here in the denominator we'll get 2 sine square d by 2 minus 2 iota sine d by 2 into cos d by 2. Now in the numerator we'll take sine n d by 2 common, and in the denominator we'll take sine d by 2 common. So we'll take them common. We can write this sum as sine n d by 2 upon sine d by 2 into e to the power iota a, and here we'll get sine n d by 2 minus iota cos n d by 2 upon sine d by 2 minus iota cos d by 2. We have already cancelled this 2 with 2. Now here what we'll also do is we'll take minus iota common from the numerator, and we'll take minus iota common from the denominator. So minus iota and minus iota will cancel. So we can write this as sine n d by 2 upon sine d by 2 e to the power iota a, and if we'll take minus iota common, we'll write this cos term first. So it'll be cos n d by 2, and then this is iota to the power 4. If we'll take iota cube common, we'll get this as plus iota sine n d by 2. And in the denominator, we'll have cos d by 2 plus iota sine d by 2, which is nothing but sine n d by 2 upon sine d by 2 e to the power iota a, and this is e to the power iota n d by 2 upon e to the power iota d by 2. We can write this as sine n d by 2 upon sine d by 2, and here it will be e to the power iota. Now this is a plus n minus 1 into d by 2. So we can write this as sine n d by 2 upon sine d by 2, and this is cos a plus n minus 1 d by 2 plus iota sine a plus n minus 1 into d by 2. Now this s is x plus iota y. So its real part is x and its imaginary part is y. So if we compare, we'll get this x as sine n d by 2 upon sine d by 2 cos a plus n minus 1 d by 2, and y is sine n d by 2 upon sine d by 2 sine a plus n minus 1 d by 2, which proves our formula. So these are the two methods with which we can prove this formula. Now let us take some questions where we'll be using this formula. Now here the question is, find the value of sine pi by 7 plus sine 2 pi by 7 plus sine 3 pi by 7. Now another way to solve this question is using formula for sum of series of sine when the angles are in AP. So these three angles, pi by 7, 2 pi by 7 and 3 pi by 7, they are in AP. And in this case, first term is pi by 7. Common difference is also pi by 7, and the value of n is 3. So we'll use the formula. We know that formula is sine n d by 2. So sine 3 and then d by 2 is pi by 14 upon sine d by 2, which is sine pi by 14 into sine a, which is pi by 7 plus n minus 1, which in this case is 2, into d by 2, which is pi by 14. So we'll get this as sine 3 pi by 14 into sine 2 pi by 7 upon sine pi by 14. Now we'll multiply with 2 and we'll divide it with 2. We can write this as 2 sine A sine B, which is cos A minus B minus cos a plus b. So we'll write this as cos a minus b. So cos a minus b here will be 3 pi by 14 minus 2 pi by 7 and then minus cos a plus b, which is 3 pi by 14 plus 2 pi by 7 upon 2 sine pi by 14. Now this is cos, here it will be 3 pi minus 4 pi minus pi by 14 and cos minus theta is plus cos theta. So it will be cos pi by 14 minus cos. Now this is 3 pi by 14 plus 4 pi by 14, which is 7 pi by 14. So it will be cos pi by 2 upon 2 sine pi by 14. Now cos 90 is 0. So it becomes 1 by 2 and cos upon sine is simply cot. So it is 1 by 2 cot pi by 14, which is your option B. Now let us take another question. And the question is, let z equals cos theta plus iota sine theta. Then the value of summation m varies from 1 to 15 imaginary part of z to the power 2m minus 1. So we can write this as summation m varies from 1 to 15 imaginary part of cos theta plus iota sine theta to the power 2m minus 1. Now using De Moivre's theorem, we can write this as summation m varies from 1 to 15 imaginary part of cos 2m minus 1 theta plus iota sine 2m minus 1 theta. Now its imaginary part is sine 2m minus 1 theta. So we can write this summation as summation m varies from 1 to 15 sine 2m minus 1 theta. Now we'll expand this series. This series, it becomes sine theta plus sine 3 theta plus sine 5 theta up to 15 terms. Now here again angles are in AP. Here the value of A is theta, value of D is 2 theta and value of N is 15. So if we use this formula for sine, formula is sine n d by 2. So it will be sine 15 and d by 2 is theta upon sine d by 2, which is sine theta, into sine A, which is theta, plus n minus 1, which is 14, and d by 2 is theta. So we can write this sum as sine 15 theta into sine 15 theta upon sine theta. So the value of this summation will be sine square 15 theta upon sine theta. And the question, it says at theta equals 2 degrees. So the value of theta is 2 degrees. So we'll put theta as 2 degrees. We'll get this as sine square 30 degrees upon sine 2 degrees. Now sine 30 is 1 by 2. So this value will be 1 by 4 sine 2 degrees, and that's your option D.
Now here the question is, for non-negative integers n, let fn be equal to this summation k varies from 0 to n sine k plus 1 upon n plus 2 pi sine k plus 2 upon n plus 2 pi whole divided by this summation k varies from 0 to n sine square k plus 1 upon n plus 2 pi. Now what we'll do is we'll multiply and divide everything with 2. Now this is 2 sine A sine B. So we can write this fn as cos A minus B.
Now cos a minus b, if we subtract k plus 2 minus k plus 1 is simply 1. So it'll be this summation k varies from 0 to n, and this is cos pi upon n plus 2, and here it will be minus cos a plus b. So if we add them, we'll get cos 2k plus 3 upon n plus 2 pi. So we have this in the numerator, and in the denominator it is 2 sine square theta, and 2 sine square theta is 1 minus cos 2 theta. So it will be this summation k varies from 0 to n 1 minus cos 2k plus 2 upon n plus 2 pi. Now we simplify this summation. This term it is constant, so it will be this fn equals n plus 1 cos pi upon n plus 2 and minus this summation k varies from 0 to n cos 2k plus 3 upon n plus 2 pi divided by, and this is summation 1, which is n plus 1 minus this summation k varies from 0 to n cos 2k plus 2 upon n plus 2 pi. Now both these sums, they are sum of cos series when angles are in AP, and we know that cos alpha plus beta cos alpha plus 2 beta up to cos alpha plus n minus 1 beta. That means when angles are in AP and number of terms is n, this series is equal to sine n beta by 2 upon sine beta by 2 cos alpha plus n minus 1 beta by 2. So this is the formula which we are going to use here. Now in this one, if we put k as 0, we'll get alpha as 3 pi upon n plus 2, and here beta, it will be common difference, and common difference is 2 pi upon n plus 2. And for the series in the denominator, first term, if we put k as 0, it will be 2 pi upon n plus 2, and its common difference, if we take two terms and subtract, we get 2 pi upon n plus 2. Now in this first series, number of terms is n plus 1, and the second series also, number of terms is n plus 1. So now we will use this sum of AP formula. So this Fn will be n plus 1 cos pi upon n plus 2, and this is minus, and this is sine n beta by 2. Now n here is n plus 1, and beta by 2 will be pi upon n plus 2 upon sine beta by 2. So it will be sine pi upon n plus 2 into cos alpha. Alpha is 3 pi upon n plus 2 plus n minus 1, and n minus 1 in this case is n beta by 2. So there will be n pi upon n plus 2 divided by, this is n plus 1 minus, and this is sine n beta by 2. So there will be sine n plus 1 pi upon n plus 2 upon sine beta by 2. So it will be same term because beta is same in both the series, sine pi upon n plus 2, and then we have cos alpha here is 2 pi upon n plus 2 and plus n minus 1 beta by 2, which again is n pi upon n plus 2. Now if we look closely, then if this is A and this is B, then clearly a plus b will be n plus 2 pi upon n plus 2. So we'll have this as pi. Then we can write b equals pi minus a. Then sine b, it is equal to sine a. Essentially, these two signs, they'll have same values. So we can cancel them in the numerator and we can cancel them in the denominator. Now we'll get this as fn, and it is equal to n plus 1 cos pi upon n plus 2 minus, and this is cos n plus 3 pi upon n plus 2, and this is n plus 1, and minus this is cos pi. Now we can write n plus 3 upon n plus 2 pi as pi plus pi upon n plus 2, and cos pi plus theta is minus cos theta. So we can write this as n plus 1 cos pi upon n plus 2, and this is plus cos pi upon n plus 2, and cos pi is minus 1, so that will be n plus 2. So we'll get this as n plus 2 cos pi upon n plus 2 upon n plus 2. Now this n plus 2 will cancel. So our function fn, it is nothing but cos pi upon n plus 2. So our function fn is cos pi upon n plus 2. Now we need to find which of the following options is correct. First is option A. For option A, we need to find f4. Now f4 is cos pi by 6, and cos pi by 6 is under root 3 by 2. That means this option A, it is correct. Now for this option B, we have alpha equals tan of cos inverse of f6. Now this is tan of cos inverse. Now what is f6? f6 is cos pi by 8. Now cos inverse and cos will cancel. Now this is tan pi by 8, and we know that tan pi by 8 is root 2 minus 1. So we can write alpha plus 1 equals root 2. We square it. We can write alpha square plus 1 plus 2 alpha equals 2, or alpha square plus 2 alpha minus 1 equals 0. That means this option B is also correct. Now coming to this option C, we're going to look at sine 7 cos inverse f5. So it will be this sine 7 cos inverse. Now what is f5? f5 is cos pi by 7. Now cos inverse and cos will cancel. Now the 7 will also cancel. Value of sine pi is 0. So that means this option C, it is also correct. And then we have this option D, where we have this limit n tends to infinite fn. So it will be this limit n tends to infinite and cos pi upon n plus 2. Now this is cos 0, and cos 0 is 1, not 1 by 2. So the only options correct are A, B and C. Now similar to telescopic summation, we have telescopic product. Now in telescopic product, we use ratios. Say for example, we have this product where R varies from 1 to n, A R upon A R plus 1. Now if we expand, if R is 1, it'll be A1 upon A2, then it'll be A2 upon A3. I'll continue up to AN upon AN plus 1. Now here these successive terms, they'll cancel. We'll get this as A1 upon AN plus 1. So basically it is multiplicative version of telescopic summation. And if it is AR plus 1 upon AR, then basically it'll reverse. So it'll be AN plus 1 by A1. So if we take an example, suppose we have this product. K varies from 1 to N, K upon K plus 1. Now when the value of K is 1, it is 1 by 2. Then K is 2, it'll be 2 by 3, 3 by 4. And it'll continue up to N upon N plus 1. All these terms, they'll cancel. We'll get this as 1 upon N plus 1. And if we use the shortcut, when K is 1, this is A1. So it'll be this 1. And N plus 1 will be simply N plus 1. So this is 1 upon N plus 1. Let's take another example. Suppose we are given this product. K varies from 2 to N, K square minus 1 upon K square. Now here we can write this as this product. K varies from 2 to N, K minus 1 upon K into K plus 1 upon K. Now basically this is this product. K varies from 2 to N, K minus 1 upon K into this product. K varies from 2 to N, K plus 1 upon K. Now if we telescope them separately, this first one will be 2 minus 1, 1 upon N. And this second one, now it is AR plus 1 upon AR. So it will be this N plus 1 upon 2. So this product, it will be N plus 1 upon 2N. So basically in telescopic summation, subtraction cancels in sums. And in telescopic products, ratios cancel in product. Now we may have shifted linear telescopes. Say for example, we are asked to evaluate this Pn, and this is this product. R varies from 1 to N, R plus 2 upon R plus 5. Now between 2 and 5, there is a difference of 3. So this is not exactly AR and AR plus 1. So if we expand this, it'll be 3 by 6, 4 by 7, 5 by 8. And in the end, it'll be this N plus 2 upon N plus 5. Now next one will be 6 by 9. So terms, they'll start cancelling after first 3 terms. So in the numerator, we'll have 3 into 4 into 5. And if this first 3 terms, they did not cancel in the numerator, that means there'll be 3 terms in the denominator in the end, which will not get cancelled. So it'll be this N plus 3, N plus 4, and N plus 5. So basically it is 60 upon N plus 3, N plus 4, N plus 5. Now there could be problems where the term, it may not exactly look telescopic. Say for example, this problem. We are given this Pn, and it is this product. K varies from 2 to N, K cube minus 1 upon K cube plus 1. Now if we try to write first few terms, now when K is 2, it'll be 8 minus 1, 7. And this is 9. Then if K is 3, 27 minus 1, 26. And here will be 28. So it feels like we are getting different kind of terms which are not getting cancelled. But if we expand it like this, by K varies from 2 to N, this is K minus 1, K square plus K plus 1, K plus 1, K square minus K plus 1. Now we know that these two, they are related and they are shifted by 2. So it's a linear shift by 2. But what about the second one? So if we look at the second one also, this k square minus k plus 1, it can also be expressed as k minus 1 square plus k minus 1 plus 1. And you can verify it also. If you're going to expand it, it will be k square plus 1 minus 2k plus k minus 1 plus 1. So it will be this k square minus k plus 1. So this k square minus k plus 1, it is related to the previous term of k square plus k plus 1. So here also we have this telescopic product. So what we'll do is we'll write this as this product. K varies from 2 to n, k minus 1, k plus 1, and here will be this product. K varies from 2 to n, k square plus k plus 1 upon k square minus k plus 1. Now we know that since there is a shift of 2, so we'll have 2 terms in the numerator. So if we put k as 2, it'll be this 1 into 2. And then in the end, we'll have 2 terms in the denominator. So there'll be n plus 1. And here, since terms are directly related, it should be n square plus n plus 1, because this is ar plus 1 upon ar, divided by, and when the value of k is 2, so it'll be this 4 minus 2 plus 1. So it'll be this 2 upon n plus 1. And here this is n square plus n plus 1 upon 3. So it'll be this 2 by 3 n square plus n plus 1 upon n plus 1. And if you don't get a feel of this, then you can solve them separately. So if we solve this first series, this pi k varies from 2 to n, it'll be this 1 by 3, 2 by 4, 3 by 5, 4 by 6, and it'll go up to n minus 1 upon n plus 1. Now here, these terms, they'll cancel. Now we have 2 terms left in the numerator. So there'll be 2 terms left in the denominator. So this first product will reduce to 2 upon n plus 1. And the same way, this second product, pi k varies from 2 to n, k square plus k plus 1 upon k square minus k plus 1. So if we put k as 2, it'll be 4 plus 2, 6 plus 1, 7. And here it'll be 4 minus 2 plus 1, 3. Now if we put k as 3, it'll be 9 plus 3, 12 plus 1, 13. And here it'll be 9 minus 3, 6 plus 1, 7. So these terms, they're getting cancelled. As we have seen, this k square minus k plus 1, it'll get cancelled with the previous term of this first series. So here we have this first term left in the denominator. So in the end, we'll have this one term in the numerator. Everything else will get cancelled. So this result will be n square plus n plus 1 by 3. And for suitable problems, there could be infinite products also. So say, for example, for the same problem, they may ask, find this product up to infinite, or this limit n tends to infinite Pn. Now this is limit n tends to infinite, and P we have already solved. So it is 2 n square plus n plus 1 upon 3 n square plus n. Now since this is infinite limit, degree is same. So it has a finite answer, and the answer will be coefficient of highest power of n square. We have studied all this in limits. So answer to this will be simply 2 by 3. Now every telescopic product, it can be turned into telescopic summation using logarithms. So if we have this product, suppose product of AR, and if we take log, it'll change to this summation log AR. So if this AR is log product FR upon fr plus 1, it'll change to this summation log fr minus log fr plus 1, which is simply telescopic summation. So though it is not needed, I've just illustrated the relationship between telescopic summation and telescopic product. And if you want, we can also have a direct shortcut for telescopic products also. But again, I'll tell you, it's always better to write the terms, cancel the ratios, than using a direct shortcut, because direct shortcut is only going to work if we have only two consecutive terms. If there is a linear shift, then in that case, you may have to take more terms. So if this AR is of the form FR upon FR plus 1, then this product where R varies from M to N AR, it'll be simply FM1 Fn plus 1, and if this is inverted, it'll be Fn plus 1 upon Fm.